Hello, my name is Nikolaus Doppelhammer. I'm a PhD student at the Johannes Kepler University in Linz at the Institute for Microelectronics and Microsensors. And today I want to talk about monitoring zeolite formation with moving electrode conductometry. The ultimate goal of our research is to understand zeolite formation in order to do something that we call rational zeolite design. So first of all, zeolites are nanoporous crystals that are used for a variety of applications, for instance, microsieves, catalysts, or ion exchangers. And by rational zeolite design, we mean being able to tune the properties of a zeolite the way we want them to be or want them to behave. Now, how does the nucleation or the formation process of a zeolite typically look like? In the beginning, we have aluminosilicate oligomers, which are also called the precursors of zeolites. And if we heat up this precursor soup, then at a certain temperature, the nucleation and growth process is initiated. And at the end of synthesis, we end up with our zeolite product. Now, in highly alkaline conditions, there is a specific type of condensation reactions which releases highly mobile charges such as hydroxide ions and metal cations. And due to these condensation reactions, we actually expect that we should be able to monitor the crystallization process by means of the electric conductivity. Now, a short recap for those of you who are not so familiar with the concept of conductivity. The definition of conductivity is that it's a measure of an electrolyte's ability to conduct electric current. It is a function of the ion concentration, of the ion mobility, and the ionic charge. And there are two different definitions. One is microscopic Ohm's law and one is macroscopic Ohm's law. The former actually tells us that whenever we apply an electric field, then the current density is proportional to this electric field. And the proportionality constant is the conductivity. Macroscopic Ohm's law is a little bit more useful for us engineers because it actually tells us how to measure conductivity. And this is basically the Ohm's law as we know it, which also contains the conductivity as a parameter. Now, there are two types of conductivity sensors. There are electrode sensors and inductive sensors. Due to time reasons, I will not be able to explain the sensor principles, just want to point out a few aspects of these sensors. Electrode sensors, there are 2- and 4-pole sensors. The accuracy of these sensors scales roughly inversely proportional to the conductivity. And these sensors are prone to passivation and corrosion because whenever you have, for instance, a highly alkaline or a highly acidic solution, then it can happen that your electrodes corrode or passivate, altering the conductivity measurement. Inductive sensors are different than electrode sensors. They scale, the accuracy scales roughly proportional with the conductivity. And they're inert to passivation and corrosion. They're also called contactless sensors because they are usually enclosed in a polymeric housing, for instance, PEEK or Teflon, which is highly chemically resistant and also temperature resistant. So therefore, this is not an issue, but they require quite large sample volumes. For our samples, we need the best of the two worlds, so to say. We need high accuracy at high conductivities because our samples are very ionic and very alkaline as well. It should be corrosion and temperature resistant, then inert to heterogeneity effects. This I will explain in a second. And we also want to have low sample volumes because some of our samples are not the cheapest. And it's a laboratory device where you typically want to have small sample sizes. With these requirements in mind, we came up with sensor design as you can see here. I would like to discuss the right picture here because it shows its most important parts. And actually its most important part is this counter electrode here, which is located inside a sample tube. And the counter electrode itself is mounted on a linear stage, so we can move this counter electrode up and down and vary the electrode distance. Here in the bottom is a working electrode, and the sample itself is contained in this sample tube here made out of Teflon, and all these parts are enclosed in a metal housing which maintains the temperature control. And by varying this inter-electrode distance here, we can do something that we call moving electrode conductometry. So what is moving electrode conductometry? For a better explanation, I prepared a short animation, and let's have a look at it. So here on the left you see the conductivity cell in a much simpler geometry, and the two electrodes that are connected to a potentiostate or an impedance analyzer. In the first step, we record a frequency spectrum in a large frequency range in order to determine the frequency where the phase shift is 0. At this frequency, the impedance resembles a purely ohmic resistor, and therefore we select this frequency as the measurement frequency. And then we record impedance values at variable electrode distances, plot them as a function of the electrode distance, and we see that we get a nice linear relationship. If we then approximate these points with a linear function, we can directly determine the conductivity via this equation here. As you can see, the only parameter is the slope of this linear fit here, and the parameter A, the big A, which stands for the cross-section of the sample tube. And if we do this over time, then we can, for instance, monitor the crystallization of particles, as we will see in a second. Before I come to the results, I want to mention two advantages of moving electrode conductometry versus static electrode conductometry. And I think the biggest advantage is that our measurement is independent of electrode near effects or of the electrode's geometry, as we validated here with simulations and experiments. So we tested a couple of different geometries, and we found out that they all exhibit the same linear behavior. And as we determine the conductivity not from the absolute resistance value but from the slope of the resistance, we get the same conductivity reading for all of these electrode geometries. Whereas if we would determine it from a static measurement, this would not be the same, because as you can clearly see that the absolute resistance values are different. A second advantage of moving electrode conductometry is that this method is already hardly dependent on the measurement frequency. Whereas if we would measure it statically, then you can see that when you do not choose the right measurement frequency and measure a highly ionic sample, as in this case, you already get quite high errors if you go down to lower frequencies. Whereas for moving electrode conductometry, you can go even below 10 kilohertz and still have hardly no error in your measurement. Now a few words on the cell performance. We determined the error of our measurement by measuring differently conducting samples a couple of times, and as you can see, the error is pretty small. Compared to commercial devices, this is lower than these devices, and this is also necessary because in our crystallization studies we only expect very small conductivity changes, as you will see in a second. Yeah, and now I want to show you our crystallization monitoring results. So for this we measured zeolite precursor samples with this composition. And in this sample series we varied the water content, so we went from highly ionic, highly concentrated samples to diluted samples, and put these samples into our cell at a constant temperature of 60 degrees. And yeah, here on the right you can see what we measured, and the results are already pretty interesting. So if we look at this purple line, which is the most concentrated, the case with the least water, then we can see that we have quite a different crystallization behavior than for the other three cases. Different in the sense that we have a highly asymmetric shape of this crystallization curve. And we also see two bumps here, which might point to a two-step crystallization process. Whereas the other samples show a much more symmetric shape, which points to a one-step homogeneous nucleation process. So what are the conclusions and the outlook? Due to charge release condensation reactions, we enable crystallization monitoring via conductivity measurements. Our cell design, combined with moving electrode conductometry, allows to accurately check small conductivity changes, which we saw with our crystallization study on zeolite samples. The advantages of moving electrode conductometry over static electrode sensors are, on the one hand, that the measurement is independent of the electrode geometry and electrode near effects, for instance, passivation or sedimentation effect, or also corrosion. Then we can measure in a large frequency range, and we have a high accuracy in a large conductivity range, especially for highly conductive liquids. And yeah, the outlook is that we measure more samples, crystallizing samples, and yeah, hopefully spot weird and surprising crystallization behavior. And at a later stage we want to model these crystallization curves and see if we can link them to modern or classical nucleation theories. Thank you.